Hello. So today I would like to talk about alternating series. And so the nice thing about alternating series is that there's a very nice test to see whether it's convergent or not. Again, like with the two tests we did last time, this test does not tell us exactly what the series converges to, but it does give us some sense of the error or the remainder as far as how close we are to the actual series with a partial sum. So we have some idea using this alternating series test to sort of see what's going on. So an alternating series is a series that alternates between positive and negative terms. So every other term is positive, every other term is negative. And so the way that this is achieved is that when you're looking at your sequence has a -1 to some power, and that power is either a k or like a k plus 1. And so anytime that k is even, k plus 1 is odd, and so this will be negative. Anytime k is odd, k plus 1 is even, this will be a positive 1. So the powers of -1 are either positive or -1. They're not going to change value. And so you get either positive or negative, and every other term is positive and every other term is negative. So what we basically are looking at is some sort of infinite series. So it's a sum from 0 to infinity. -1 to some power, that's either k plus 1. Here's k because k equals 0 is the first term, so it's a positive term first, and then an a sub k. That a sub k, just like we've been doing before, this a sub k is a non-negative sequence of numbers. All right, so in other words, this thing is alternating, and the a sub k doesn't have a sign. It's just positive or 0 every time. So it's definitely a non-negative term, that a sub k, and then we kind of go from this. The nice thing about these sequences or these series is that we know that the series, converges, provided that number one, the terms of the series are non-increasing in magnitude. And so it's sort of like the terms in this sequence of a sub k's are getting smaller or staying the same for some k greater than some n. And so it doesn't have to happen right away, but eventually after some point, some big number here, all the terms after there are decreasing or not increasing. And so we then have that the limit of the sequence of positive terms is 0, is the other requirement. So the two things that we need to know is are they non-increasing in magnitude, and is the sequence limit actually 0? And so if we can check those two things, then we are done. So in particular, last time we did something with this harmonic series where it was the sum of 1 over k, and we showed that does not converge. Well, the nice thing here, the alternating harmonic series, so put a sign on each of these things that alternates between positive and negative, this is actually convergent. And how do I show that? Well, I basically say I've got two things to check. So first off, 1 over k is always actually decreasing. So for all values of k to 1 to 2 to 3 to 4 to 5 to 6, so every successive term is smaller than the previous term. So this is a decreasing sequence. And then second of all, the limit of this sequence as k goes to infinity is actually 0. Okay. And those two things, as long as I can check those two things, this is a convergent sequence. And it makes a lot of sense for an alternating series, because you sort of think I'm adding something, then I'm subtracting something, and I'm adding something, and I'm subtracting something. And as long as the things that I'm sort of adding and subtracting are getting smaller, these terms will be convergent to some value. So as long as sort of like the difference between those two is getting smaller and smaller and smaller, your sum of this alternating series is going to converge. So this is really nice. All right. So that's pretty cool. So what else do we need to know? So what else we would like to know is this remainder. So remember, the remainder is the actual sum. So that's the total sum minus the partial sum. And so the magnitude of this remainder is less than the next term in the sequence. Okay, so this sequence is a non-negative sequence. It's a positive sequence-ish. Basically the remainder, the difference between the actual sum and the partial sum is no bigger than the next term in this alternating, in this sequence of terms. So that's pretty cool. Basically, that means that I can give you some sort of accuracy of how close am I to the actual value of the series, right? And we will use this later on when we're talking about some series that are specifically special series that estimate things like natural log or sine or cosine. And so if you're in sort of engineering or physics or any of these sort of applications of these series, what you're really looking for is you're looking for an estimate of the value of sine of x, sine of 15. So I want to know sine of 15. Well, sine of 15, I can plug this into a calculator and that's great, but maybe I don't need that accuracy. So maybe I want to estimate this thing as some sort of like polynomial. And how close do I want it to be? Well, I can then, guarantee that I will be that close as long as I take enough terms in this alternating sequence or in this alternating series, right? So that's the idea. All right. So then the other two terms that we need to know, if I take the absolute value of every term in my sequence here and I add them all up, if that converges, I would say that the series converges absolutely. So that's a definition here. So absolute convergence means the absolute value of all the terms converges. So for example, the alternating series minus 1 to the k plus 1 over k squared. If I took it, this is definitely a convergent sequence because it's an alternating sequence. The terms go down and it goes to 0 as k goes to infinity. So that's great. And this is actually absolutely convergent because the absolute value of these terms, so the sum of the absolute value is the sum of 1 over k squared. And last time we showed that this, by the integral test, is convergent. So this converges, so it converges absolutely, right? If the sum of the absolute value diverges, but the sum of the actual terms converges, I would say it converges conditionally. So it's a conditional convergence. And so there are sequences like this, in particular, the alternating harmonic series is one of these. So if I take the alternating harmonic series, so it's k plus 1 on the top over k, this converges. But the sum of the absolute value of these things is just the sum of 1 over k, and that diverges. So we say this series converges conditionally. So we have a conditional convergence here because the absolute value of this thing does not converge, but the series itself does converge. Okay. So what's nice about this is that if I have something that is absolutely convergent, then the actual thing converges no matter what. So if I can show that the sum of the absolute values of all the terms converges, then I can actually state that, oh, the original one must also converge. On the other hand, if I have the sum of the sequence diverges, then the sum of the absolute values also has to diverge. So those sort of go hand in hand there. Notice what we are not saying here. So I probably don't like saying these kinds of things, but basically the sum converges does not imply the sum of the absolute values converges. So you have to sort of be very careful about this. The sum diverges means the sum of the absolute values diverge. The sum of the absolute value converges, some of the actuals converge. Okay. So let's look at an example of this. So we're looking at some examples here. So I've got an alternating series here. It's going to be natural log of k over k squared. And we want to think about terms here. So the first term of this series let's think about partial sums here. So the first term of this thing is just going to be natural log of 1 over 1 squared. And natural log of 1 is 0. So this term is just 0. So S2, and really I should be thinking of like A2 here. So A1 is just 0. A2 is natural log of 2 over 4, which is 2 squared. And that is not 0, and it is negative, right? Oh, sorry. Yeah, we'll go for that. Then the third term of this series is just going to be natural log of 3 over 9. So notice the first term is smaller than the second term, but the second term is sort of bigger than the third term, is bigger than the fourth term, is bigger than the fifth term. So we do have that first condition here. And that first condition said that a k plus 1 is less than or equal to a k for k beyond something. And so here I can say k greater than or equal to 2. So as long as we're the second term and beyond, this is a decreasing sequence. So that's good. Then what's the limit as k goes to infinity of natural log of k over k squared? So there's a couple ways you could do this. You could sort of do that growth rate thing where we said, oh, okay, the thing on the top, the natural log, grows slower than the k squared. So this limit is just going to be 0. Or I do a L'Hopital's rule, because the natural log of k as k goes to infinity goes to infinity. K squared as k goes to infinity goes to infinity. So this is infinity over infinity. I can apply L'Hopital's rule directly. So applying L'Hopital's rule directly is actually the easy way to do this. Derivative of natural log is 1 over k. Derivative of k squared is 2k. So this is really limit as k goes to infinity of 1 over 2k squared. And that is just 0. So yes, this thing actually goes to 0 as k goes to infinity. And it is a decreasing sequence for k greater than or equal to 2. So this thing converges. So it's a convergent sequence and satisfies both of those two conditions. And so we're happy with that. Okay. Let's go for the next one. So we've got cosine of k pi over k squared. And so we think about this for a second. This doesn't look like an alternating series right away, except we have to think here, what's cosine of pi? What's cosine of 2 pi? What's cosine of 3 pi? And 4 pi and 5 pi and so on. So cosine of pi is -1, cosine of 2 pi is +1, cosine of 3 pi is -1. So any odd k inside there makes it negative, any even k inside there makes it positive. So this is an alternating sequence or alternating series, and the sign comes in with the cosine of k pi. So what we need to think about here is, oh, okay, so now what about the sequence ignoring the sign? So the sequence ignoring the sign, the absolute value of this thing. So the absolute value of cosine k pi over k squared is just the sum of 1 over k squared. And we know that the sum of 1 over k squared converges. So this is actually absolutely convergent. And since it's absolutely convergent, the actual series itself is also convergent. So we would say this, so that means that the sum from 1 to infinity of cosine of k pi over k squared converges also. So that's one way we could do this. The other way you can do this is you can just say, oh, so then the sequence is 1 over k squared. It's decreasing as k gets bigger than, and that's for all k bigger than or equal to 1, and it limits to 0, therefore it's also convergent. So you sort of have two ways to do that one. It's absolutely convergent, but it's also just convergent by the two properties that we have to check. All right. How about this one? So it's an alternating series. I look at the terms here. What is the limit as k goes to infinity of k to the 18 plus 2k to the 9 plus 3 over, I'll multiply that k through, it gives me k to the 18 plus 3k. So you could either do this sort of one of two ways. I will divide by the largest power of k on the top and the bottom and then take the limit there. Or I just look at this and say the degrees are the same on the top and the bottom. So I remember from my rules from college algebra, divide the coefficients of the first two terms. And then that's how we get it. So I'll do the 1 over k to the 18 just for completeness here. So I divide all my terms by k to the 18th. All right. And so what I end up getting here is just the limit as k goes to infinity of 1 plus 2 over k to the 9 plus 3 over k to the 18 over 1 plus 3 over k to the 17. Anything with a k in the denominator in the limit goes to 0 because it's a denominator getting bigger and bigger and bigger. So I'm just left with 1 over 1. So the limit here is 1. Wait a minute. The limit should have been 0 if this thing was convergent. So this series diverges. And you can think about that. Basically, as we get bigger and bigger and bigger with the k's, I'm getting closer to 1 and -1. And so as I'm sort of adding all the terms all together, the terms are getting closer to 1 and -1. And so I'm just bouncing between adding 1, subtracting 1, adding 1, subtracting 1, adding 1, subtracting 1, adding 1, subtracting 1. And so I never, ever approach one value there. I'm just bouncing between two values, either add 1, subtract 1, add 1, subtract 1, add 1, subtract 1. So here I do not converge. And it's not necessarily going to infinity, but it's just bouncing between values here. And so that's the divergence here. All right. And that'll be true as this series and the sequence inside goes to not something other than 1. You're sort of adding, something other than 0. You're adding and subtracting that number again and again and again and again. And so you're just bouncing between two numbers there. It's a divergent sequence in that situation. All right. So the last example I want to do here is this idea of the remainder. So what I have here is I have a series. And I tell you the value of the series. I tell you the value of the series is natural log of 64. You don't have to know the value of the series to do this test, but it's nice to sort of see that this series does converge to natural log of 64. That's kind of cool, right? It's weird that this converges to something so nice, but that's what it is, right? So what are we looking at here? So we're looking at the 6 times -1 to the k plus 1 over k. I want to know how many terms do I need to take to ensure that this remainder is as close correct to 5 decimal places. Right? So 10 to the -5 is sort of like this 0.00001, right? And so I want to be that close to the actual value of this series. So what do I do? What I do is I say, oh, so remember, the remainder in absolute value is at least, there's no bigger than the next term in my sequence. So how many terms do I have to sum in order to get close enough within 5 decimal places of the actual value of this series? So what I look at here is I look at the a. So a sub k here is just 6 over k. So the a sub k ignores the sign and just takes the sequence inside there that is positive. So 6 over k is what we're looking for. And I want my remainder to be at most sort of no bigger than 10 to the -5. So where is this a sub k equal to 10 to the -5? So that's the question. So for what value of k is this thing 10 to the -5? So we plug it in. So I've got 10 to the -5 equals 6 over k. This is not a terrible thing to sort of get here. What I'm really looking at is 1 over 10 to the 5th. That'll make my life a little easier. Now I cross multiply. And so what I get is k is 6 times 10 to the 5th. And so that means that k is 600,000. Okay. And so that is like the next term. So how many terms do I need to take here? I need to take 599,999 terms to estimate this within that 10 to the minus 5th power. Okay, so we're within 10 to the minus 5th by taking 599,999 terms. Okay, and that's a pretty good accuracy. That's actually really terrible accuracy. So I have to add a lot of terms to get that accuracy. So probably if this were to happen to you in real life, you would say, I don't want to add that many terms. There's sort of no reason to add that many terms. There must be another way to estimate natural log of 64 that's more convenient, that's easier, that does not take quite as many things to add up to get to that. Okay. And so this is, again, sort of the laziness of a mathematician coming through. Sort of you can figure out like how much work am I going to have to do, and then you decide I don't want to do that amount of work. Let's find a different way to do it. So that's the sort of it's honestly what drives mathematics a lot. We're all kind of lazy, and we all just want to do the best we can, and so we evaluate these things, or we figure out how many things we need to do, how much work do I need, and then I try to figure out, how can I avoid that work? And so that's good. All right, cool. So that's that for today. And then next time, we're going to talk about 2 more tests. They're like the ones we did last time, where there's not a nice exact value for the series, but you can tell whether it's convergent or divergent based on what you already know. All right, so we'll talk more next time.